In this lesson, we will introduce some showtime parameters used in speech processing. Most of the showtime parameters are computed in time domain, including showtime energy, showtime magnitude, and showtime zero crossing rate. The showtime autocorrelation and showtime average magnitude difference function are often used to estimate pitch cycle for voice speech, which will be introduced in next session. One parameter is showtime energy. The long-term definition of signal energy is the sum of squares of input signal samples. There is little or no utility of this definition for time-varying signals. Thus, we use showtime energy in vicinity of time n and compute the sum of squares of L samples. Generally, the showtime processing window is said to be rectangular when computing the showtime energy. Showtime energy can serve to differentiate voiced and unvoiced sounds in speech from silence, background noise. We can also use the natural definition of energy or weighted signal. At this time, the energy in showtime interval comes to be the sum of squares of portion of signal. This processing can concentrate measurement at sample n using weighting function. The weighting functions can be different shapes of windows. Another form is the sum of squares of weighted input signal with function hn. If the input signal samples at rate fs and r is the frame shift, the showtime energy with different windows can output a series of parameters en with rate fs divided by r. Considering two kinds of windows, rectangular and Hamming window, the showtime energies using different windows are also different. As the frame length L increases, the plots tend to converge and the sound energies are smoothing. Showtime energy provides basic for distinguishing voice from unvoiced speech regions. And for medium to high SNR recordings, can even be used to find regions of silence background signal. Showtime energy is very sensitive to large signal levels due to the square of input signal. We consider a new definition of pseudo-energy based on average signal magnitude rather than energy. It is a showtime parameter with weighted sum of magnitudes, rather than weighted sum of squares. The computation avoids multiplications of signal with itself, the square term. The input signal xn is transformed to absolute values firstly, and then multiplied with weighted function wn. Considering two kinds of window, rectangular and Hamming windows, the showtime magnitudes perform different. As the frame length L increases, the function of showtime magnitudes are smoothing. The parameters of showtime magnitudes can also be used to distinguish voiced and unvoiced speech. The differences between showtime energy and showtime magnitude are noticeable in unvoiced regions. Dynamic range of showtime magnitudes is relative to the square root of dynamic range of showtime energy. The level differences between voiced and unvoiced segments are smaller. Showtime energies and showtime magnitudes can be sampled at a rate of 100 per second for window durations of about 20 milliseconds, which can lead to efficient representations of signal energy or magnitude. Zero crossing rate is a simple measure of the frequency content of a signal, especially true for narrowband signals. For example, sinusoids. Zero crossing is counted when successive samples have different algebraic signs. Sinusoid at frequency f0 with sampling rate fs, hence fs divided by f0 samples per cycle, with 2 zero crossings per cycle, giving an average zero crossing rate of z1, shown in the equations. Then we can get the average zero crossing rate with m samples. We can define ZC rate with symbolic function sign, similar with short-time energy or magnitude. The short-time average ZC rate can be described with the generic flowing chart. Wn is window function, which can be regarded as low-pass filter. Zero crossing for noise signal is higher than that of the periodic signal. The figure shows zero crossing of random Gaussian noise. We can see that ZC rate will be lower if there is DC direct current offset. As is shown in the figure, the short-time energy function describes the envelope of the waveform. ZC function has opposite trend with the energy function. When the frame or window length L is increased, the functions are smoothing. As is shown in ZC rate distributions, energy is mainly below 1.5 kHz for voice speech, and dominant energy component is at about 700 kHz. For unvoiced speech, energy is mainly above 1.5 kHz, and the dominant energy component is at about 2.5 kHz. Mean ZC rate for unvoiced speech is 49 per 10 millisecond interval and is 14 per 10 milliseconds interval for voiced speech. From the figure, we can see that ZC rate can be used to distinguish unvoiced and voiced speech under most circumstances. In most cases, the energy of voiced sound is concentrated in the lower frequency band and hence a lower zero crossing rate, while the energy of unvoiced sounds is concentrated in the higher frequency band and hence a higher zero crossing rate. This slide shows a summary of simple time domain measures, including short-time energy, magnitude, and zero crossing rate. There are also other forms of short-time parameters, or the frequency analysis of speech signal in short-time intervals. A segment of speech signal and its normalized short-time energy, short-time magnitude, and short-time zero crossing rate curve are shown in the figure. The diagram shows the conditional probability density of the short-time amplitude and short-time average zero crossing rate in three cases: silence, unvoiced, and voiced. It can be seen that the short-time amplitude of voiced sounds is the largest, and the short-time amplitude of silent sounds is the smallest. The short-time zero crossing rate of unvoiced sounds is the largest, Silent is in the center, and the show time zero crossing rate of voiced sounds is the smallest. The probability distribution has overlapping parts, which means there will be misclassification for mixed type of signals. Sometimes all the three parameters are combined to do the UVS classification: VAD, voice activity detection, or voice endpoint detection. That's all for this session. See you next session.